Hey dudes, we are into it. We are starting differentiation from first principles. First principles. Before we jump into it, I think this warm-up problem will help when we get into the nitty-gritty. You probably recognize this problem from something like this evil paper from last year. You remember like working through tons of those, and one of them looked like this. Ing. And here's another one right on your screen that's a similar problem. And you were doing calculus. Little did you know. So let's revisit this. So this is like the main problem. If f of t is t squared, then find this mess. And that just sounds like intellectual punishment. But let's forget about this piece for a while and try it with some easier numbers, right? If this is f of t, just t squared. F of 3 really is 3 squared, so 9, right? No big deal. F of k is really k squared, right? F of x plus 2 is really x plus 2, the whole thing squared. Don't be the chump that drops that in there. It's x plus 2 times itself, right? It's this. All right, and so it's x squared, and 4x and 4, right? And then this is the same thing. This is f of t plus h is just t plus h squared, and you expand it like that if you like, or you can just call it t squared. You get a t and an h, and you get two sets of those, 2th and h squared. Cool? That's just how functions and distribution work. So let's take that idea and run with it. And let's get rid of this piece. Let's think about this mess. This is the same thing. We're just trying to find f of t with some other pieces in it. So this f of t plus h, this component, is really just t plus h squared, right? So it's t squared and 2th and h squared. Cool. And f of t is just t squared, right? Minus t squared. And then it's all over h, right? So if we clean that up, the t squareds cancel out. Hey, there's an h in each of these, so we could factor out an h, or we could just cancel it with this one and this one if you like. And this turns into 2t plus h, right? Cool. All right, so let's take that and run with it. All right, so I think one of the easiest, most approachable ways to calculus is in rates of change. And rates of change, I think of as speed. It's your distance traveled over the time it takes. And if you're driving in your car a very specific speed, you'd change your distance over time. Right? You'd say you'd go in 1 hour you change 60 kilometers. And this slope, right? Slope is rise over run. It's distance over time. The distance is 60 kilometers in 1 hour, right? It's a rate of change. It's a speed. You don't often drive just like in a straight line for a prescribed amount of time. You stop. There's lights. There's old people driving, right? You have to stop and go. And so often your speed isn't a nice continuous line. Sometimes you still want to be able to find how fast you're going at any one time, right? So you don't get the flash and the thunder of the Swiss speed traps. And that's kind of what your speedometers do, is figure out how fast you're going at any one time. And what you can do with how you can do that is, even though there's no straight line here, you can pick a point that you're interested in at time, whatever, t, and make a slope there. And to make a slope, you could think about just drawing a line that hits that spot once, just kind of kisses it and moves along. If it hits it more than once, right? Like if it hits there and there, or maybe let's try to get a better hit there and there, you can see it hits in sort of 2 spots. Maybe that doesn't approximate it as well, and so we really want it to just touch in one little spot as we go along. Cool. This instantaneous rate of change is really the slope of that line, right? It's the slope of this line. It's the rise over run. that's what slope is, rise over run. Okay, so instantaneous rate of change is the slope of this tangent line, the gradient. All right, so let's mess with that a little bit. So you're throwing something out a window, like your really old computer monitor, and we want to see how far it moves, how far it falls in a certain time. Here, throw me out the window too. So here's you throwing it out the window, and here's time at 2 seconds, how far has it gone? 20 meters. 4 seconds, how far has it gone? 80 meters. This would happen a lot faster if you're actually throwing something out the window, but if we want to find like the average speed for that, you could figure out like this point and just, or any 2 points, maybe this point and this point, and find the slope between them. From 2 to 4 is a change of 2 units, and from 20 to 80 is a change of 60 units. Oops, sorry. 2 to 4 is a change of 60. So this is where they get 60 over 2, so 30 meters per second. So it's saying on average between these 2 points, between here and here, your computer screen is moving this fast on average. But that's just not true. It's instantaneously. If you look at this thing, it's going to be falling a lot faster here than it is here. And one way you can see that is through the slope of their tangent lines. So if you make the slope of this, right, and it just kisses the line once, and this slope just kisses the line once also. If you kind of weasel those up there a little bit better, like that, so the action line might be too steep, like that. Who's got the steeper line, right? This has a certain rise over run, and this has a different rise over run. This is a steeper line, meaning that it's going faster there, which makes sense. So this is a good approximation, but specific time we need instantaneous speed. We need tangents. Great. So here's just some vernacular, some vocabulary. A chord on a curve is from a point to another point and goes through the body, joining the curve. A tangent line hits only once and just swoops in, kisses the parabola, and leaves. Story of my life. So tangent, chord, there you go, write those down. Single point, 2 points. All right. So this is kind of the whole idea behind calculus, behind one component of calculus. There were 2 dudes, Sir Isaac Newton and Gottfried Leibniz, who were co-inventors, they say. Now they say that one invented it 8 years before the other, but the idea is that there was need for this mathematical tool at the same time, and people just thought this up, which is neat. And that's kind of what we're going to do today, is figure out how they figured it out. And it sounds spooky, but it's not that hard. One of the goals of calculus is to figure out the slope of a curved line, right? For basic purposes, we can figure out how fast you're going at one time, right? On a non-linear curve. Lots of other applications, and we'll get into those later. Some of you have already started them in physics. Here's another one, maybe. Maybe you're talking about how much your product costs, and the more it costs, the more money you'll make, but the fewer people that will buy it. If it doesn't cost anything, lots of people will buy it, but you don't get any money from it. So maybe this is talking about like revenue and your cost. At some spot, there's a maximum, there's a sweet point, and it has a really specific slope there. Its slope is 0. And so those are interesting spots we want to see. Like slope is 0 has some good connotations. It's where we have a maximum or maybe a minimum. So doing calculus, we'll talk about what that means. Calculus analysis on these things can find interesting points, like where do you have 0 slope, meaning and where is there a maximum. But our goal today is to figure out how to give the slope in a specific spot at a specific time. Okay, so that's pretty easy if you have a contrived situation like this. Like, oh, here's the curve, and the tangent line happens to go through this point, and also this point, and just kisses the parabola once. So what's the slope, right? What's the slope at 4? That's what this is actually saying. This f prime asks for the derivative, the slope. We'll get into that in a second. And so what's the slope? Well, it's rise. This spot is 2, comma 0, and this is 6, comma 4. So it rises 4 and runs 4, right? So from 0 to 4 is the rise, from 2 to 6 is the run, and so its slope is 4 over 4. Its slope is 1, so the derivative at 4 is 1. Neat. Okay, we're going to try that in a more specific way, but let me give you an idea about how to do that. Like it's really easy if they give you the equation for the tangent line, but that doesn't always happen, right? So sometimes we have this situation where you need to figure out the tangent on your own, and one of those ways is take the point in question. Like, I want to know the slope right here, and I don't know another point there, and I don't know another point there. But let's take that same point and let's pick another point on the curve itself, right? And then this, we can take that as the slope of our line. So I don't know how big that is, but let's just try some points. Like if we used x as 5, right? We're putting it into our original equation, x squared, so you'd have 1, you'd put 1 in here, you'd get 1 squared, you get 1 out, so that's where this 1 comes from. If you put in 5, you'd put 5 in here, you'd square that, and you'd get 25. That's where this comes from. So if this is 1, and this is 5, 25, the slope is, well, let's see, rise is from 1 up to 25, that's the rise of 24, and from 1 over to 5 is a run of 4. So 24 over 4 is 6. That's where this comes from. Okay, so that's the gradient. Now maybe 5's too far away, right? This is at 1. Let's get closer. Let's instead of going at 5, let's call this 3. So let's bring this point, like 5 was up here, let's bring this point a little bit closer to 3. So this would be 3. 3 squared would be 9, so here's our new point, is at 3, 9. And now let's look at the slope of that thing, right? If we did the same game, right? 1 to 9 is an increase in 8, and 1 to 3 is an increase in 2. Our slope is now 4, right? Well, let's bring that dot even closer. Let's bring it to blue. Let's bring it to 2, like that, right? So now if we put 2 in for x, you'd put in 2, you'd get 2 squared, you get 4, and so this would be 2 comma 4. The rise would be 3 and the run would be 1, so it's coming down. Our slope is coming down a little bit, narrowing in. Let's get really close, get 1.5, right? Let's really wedge this in here, sorry. So here's 1.5. If we do that same game, we'll get 1.5 and 2.25. And if you play the same game with slope, your slope becomes 2.5. Now I'm going to start going faster because I've done the calculations already. If you use 1.1, bring the x dot really close to the 1, comma 1, you get 1.21. Slope becomes 2.1. If you get really close, slope becomes 2.01. If you get really, really close, slope becomes 2.001. It's converging on which number? Yeah, 2, right? It's converging on 2. And it looks like if we keep doing this and bringing this dot closer and closer to our target dot, our slope becomes more and more like the actual tangent, right? And this is the whole idea behind calculus, finding the derivatives. So if we here's our A, we want this actual tangent line. If we start up here, this is really different than our tangent line, right? But if we get closer, right, with our B value, it more closely approximates the tangent line, right? So these still aren't very good, but if we're using this, now we're getting better. And if we use this, now we're getting better. And if we use this, now we're getting really close to what the tangent should be. And we can do that mathematically without doing that graphically, like this, using the idea of limits. So you could think about this. as you take this point was y comma x, right? So here's our y value. We want the slope. Slope is just change in y over change in x, right? Slope is change in y values over change in x. How do you get a change? You say y2 minus y1, right, over x2 minus x1. That's just what slope is, right? So this is nothing fancy. So don't worry about this limit for a second. This says, hey, what's the slope of this line? Well, it's the y values subtracted, right? So here's y2 minus y1. This is just rise. And here's x2 minus x1. This is just run. It's rise over run. So if we clean this up a little bit, this top thing you could factor into x plus 1 and x minus 1, and then you could cancel out the x minus 1s, and you're just left with this piece. We're just doing some algebraic simplification. We can still kind of ignore this limit part for a second until we get here. Say, okay, well, what this is saying is I can't bring this dot all the way to here, right? Or else we have no slope. But I can see what happens as it gets closer and closer and closer, and that's what a limit is. So I want to talk about what's the limit as x approaches 1, right? So as x gets closer and closer to 1, this whole value gets closer and closer to 2, right? Because if you put in 0.994x plus 1, that's really close to 2. And so the limit approaches 2, and so therefore our slope is 2. That's the idea behind this. What we're doing is called the derivative function. You see it often like this. This is f prime x, or they say f dashed x. I like prime, f prime x. Use whichever you like. And f prime of a is the slope of the tangent to the curve at point A. So here's f of x, that's this blue curve. And if we are looking for this point, and this point is A, this tangent has a gradient, a slope, right? And that slope is f prime of x, or sorry, f prime of a, right? The derivative of f at a is the slope of the tangent line at point A. It sounds like a mouthful, but it's not a super complex concept. Let's try one out. We want to look at this, consider this function f of x. I don't know the equation for it, and it doesn't really matter. If we put in some value x, right, we should get out some y value, also known as f of x, right? So here's x, and here's f of x and y. Okay, fine. If we add some distance, some h, to this new point becomes x plus h. And the corresponding y value will be f of x plus h, right? It's f of whatever this is. If you don't like x plus h, call this b, right? And so then this would be f of b. And b is just x and plus whatever we added to this distance h to it, right? I'm going to keep calling it x and x plus h, and f of x and f of x plus h. All right, so we've got 2 points, x and f of x, and x plus h and f of x plus h. Cool? If we're looking for the slope is just the rise over run, right? The derivative is the slope, right? I want the slope of this chord, and because I think it'll help me approximate the tangent line as b gets closer and closer to a. So I know slope is the rise over run. It's the change in y's over the change in x's. So the change in y's are really like y2 minus y1. So it's really these two subtracted. And the run is the x2 minus x1. So it's really these two subtracted. Right? And that's all this piece is. This looks scary, but it's not. Right? This piece is the y2 minus y1 and x2 minus x1. Is that okay? All right. So let's boil that down just a little bit. If we clean this up, if we clean this top part up, this is x and negative x. Those cancel out. You're just left with h. Yeah. And so you end up with this ugly mess. And what they say is that the gradient of the tangent at this point is the limit of this as h goes to 0. And what all that jargon means is when h goes to 0, it means when this distance gets smaller and smaller and smaller. So first b is here, and then we want b to be here, and then here, and here, and here, and here, and here. And once h gets tiny, tiny, right? Once h becomes minuscule, you can really start to see what the tangent line should be. And that, therefore, is the gradient of that line gives you the slope, the instantaneous velocity, if you will. So here's the long-winded version, or maybe the short-winded version. The derivative function, or just the derivative of a function, looks like this, right? And this is called working from first principles, which means I take the change in the y values divided by the change in the x values. The change in the x values, by definition, is h. It's how we're changing, right? And so if we look at the change in y's and the change in x, we take the limit of that as h gets smaller and smaller and smaller. That's going to be the slope, right? The derivative is the slope of the tangent, right? The slope of the tangent. All right, let's put it in practice. It sounds a lot scarier than it is. So use the definition of f prime of x to find the gradient of x squared. Okay, well, if we know that f prime of x is the limit of, as h goes to 0, of the change in y's over the change in x's. If you plug in what you know, I know that this x plus h, if we're going to put that into the f function squares it, just like this game. Oop. Just like this, right? We put this in, squared it, subtracted this, and we cleaned things up. We're going to do the same thing here. So squaring this, you get x squared 2hx and h squared. The x's cancel out, and you're just left with this piece. The h's cancel out, and you're left with this piece. And we're talking about a parabola, or a curve, and our 2 points on the curve are getting closer and closer to each other. So as h approaches 0, right, as this point gets scooted down here, our chord becomes more and more like our tangent line. And so what happens as x becomes 0? What's the slope? Well, it's 2x, right? As h gets closer and closer to 0. Cool. This piece here just means that h can't be 0 because it's in the denominator. But we can imagine what happens as we get closer and closer to it. All right. So this is the alternate notation. Sometimes, well, here, pause me and read it if you like, but here's my synopsis that I think is a little bit more straightforward. This is a function, right? F of x is a function. The derivative we call f prime of x or f dash x. Sometimes they give you the function as y. Often you'll see the derivative called y prime Or sometimes you'll see it as dy dx. Often you'll see it as dy dx. This is sort of a formal way to do it. This is kind of a shooting from the hip, cool way to do it. So dy dx means the derivative. So does y prime, so does f of x prime, f prime of x, sorry. This is not a slope. It's not a fraction. It's a slope, right? You're not gonna break this apart and do math. This represents the slope like this. F prime of x should be the slope of the tangent line at some point. Slope is change in y over change in x, and change in y over change in x is what dy and dx means, right? It's this change in the y values over the change in the x values. It's like delta y and delta x, right? Change in y, change in x. Okay, so those are just some different ways to look at it. Let's try this one. So I want to take using first principles. What's nice about this is first principles means that there's easier ways to do this, but we'll get there soon enough. Here's our function. I want to find the slope at x, right? Instantaneous rate of change means find the slope at x is 5. Okay, fine. So I know that we can plug in our equation, right, into this first principles idea, right? We want to take f of 5 and change it a little bit, right, and then divide by that change. If we take f of 5 plus h, that means we square the x, right? Our x in this case is 5 plus h. We square that, and then multiply 2 times that x, so 2 times this piece, right? So this is this. And this 35 is just f of 5, right? It's just this. F of 5 is put 5 into here. 5 squared plus 2 times 5, that's 35, right? So that's this piece. That's this piece. Okay, if you expand this, you have to expand this piece into all of this. You expand this into all of this. Here's negative 35 hanging out the back. You start canceling things out. It turns into this. You cancel some h's and it turns into h plus 12. Okay, and we want to know what happens. The slope is what happens when h approaches 0. So when h approaches 0, this gets smaller and smaller and smaller. The slope approaches 12. One way you can look at that is like this. If you Desmosed this up, let's group this and move it a little bit. If you Desmosed this up and thought about it like a graph, said f of 5, here's my point 5, and that's 35 just like we thought. Right, so this is 5 comma 35. One way to approximate the slope is to pick another point. So like pick this point that's a certain distance away. So this is what, 5, 6. This is 1 unit away, and now it's at 48. Yeah. So this is a certain change. As this point, and so our line, our slope, our chord would look like that, right? As this point gets closer and closer and closer and closer to 5, the slope more and more closely exemplifies the tangent at 5. Right? Now we can't put this at 0 physically because we can't divide by 0 here, but we can think about the limit as they approach each other. And so that slope is 12, right? Once you pick the smallest interval possible, this between here, this rise over run is 12. And so that's what our slope is, okay? I know that's a lot to digest. It's the first principles, so it'll smooth out, but that's like the big picture behind it. Give it a shot with these problems, and we'll go from there when I see you.